Hi everyone, in this video we are going to consider the case of two long straight parallel current carrying wire. So we know by now that a current carrying wire in a magnetic field will be subject to a magnetic force. We also know that a current carrying wire will also create a magnetic field. So if we have two of them, they will have a force between them. All right, so let's have a look at two diagrams that I've drawn. We will start with the first one over here. We have two current carrying wire, and in both cases the current is going into the board. Because they both have a current inside of them, they will create a magnetic field. Now let's look at the wire on the left. So note I gave the notation for the wire on the left to be the first wire, this one to be the second wire. Also, when we switch to my second diagram, same logic. The left one is one, the second one, the right one is the second one. All right, so let's use the right-hand rule to determine the direction of our magnetic field. We point the thumb toward the current, the direction of the current, and the curl of our finger tells us the direction of the magnetic field. In this case, it is clockwise. Since the second wire is to the right of the first one, the magnetic field at this point will be pointing downward. Now note, we've seen in the previous section, if we want to know the direction of the magnetic force, what we need to do is we need to point our finger toward the current, curl toward the magnetic field, and our thumb will be pointing in the direction of the force. In this case, the force will be pointing to the left. Now, there's a point I want to mention also, is because this will be important in the formula after this. This is B1, so it's the magnetic field created by the current in my first wire. Okay, that's important. Now note, this is the force on the second wire is pointing toward the first wire. Okay, let's consider the force on the first wire. Now, they both have a current going in the same direction, so you can imagine we could take the circle and just move it. And since this wire is on the left of this one, the magnetic field will be pointing upward. So that means we point our finger toward the current, curl our finger toward the magnetic field, and the thumb is pointing the magnetic force. It's pointing to the right. Now actually the second step was not even needed. If we have a force acting on this wire, pulling on the first wire, and this force is coming from the first wire itself, well, by Newton's third law, the other force has to be exactly the same, but in the opposite direction. Now remember, Newton's third law is the most fundamental law in physics. We never seen any instance where it is not true, and certainly this is not the case. All right, so what we see here is if we have two wires with the current going in the same direction, the wire will be attracted to each other. If you want, you can do the same exercise with two current pointing outward, and you will see that they will be attracted to each other. Now let's consider a case of a current going in exactly opposite direction, like this one over here. So we have our first wire, the current is coming out of the board, or second wire, the current is coming into the board. Now, if we want to find the direction of our magnetic field, point the thumb toward the current, curl of our finger is the direction of the magnetic field. In this case, it's counterclockwise. Since we're considering a point over here, the magnetic field will be pointing up. So we want to find out the force on this wire over here. We point our finger toward the current, which is into the board. We curl a finger toward the magnetic field, and the force is on the right. By Newton's third law, we don't even need to test the direction of the second force. Once we have found one, we know exactly the other one. So when the current is different, in different direction, in exactly opposite direction actually, the force will be, they will repel each other. Okay, so that's an important distinction. Now, using this logic, we just found the direction of the force on themselves. The next part is we need to find the magnitude of that force, and we will combine the Biot-Savart law with the formula we derived at the end of chapter 8. So at the end of chapter 8, we saw that the force on the current carrying wire is equal to the current multiplied by the length of the wire multiplied by the magnetic field applied on it. Now there's a couple of points here. First, it's the current inside the second wire. We are looking at the force on this wire, all right? So that's important. It's an important distinction. It's this current inside that will determine the force on itself. Second, the magnetic field applied on the second wire is the magnetic field from the first one. All right. Well, it's obvious. This one is creating the magnetic field that will be on itself. Now, no, the magnetic field created by the first wire will not affect itself. All right. Now we got that term, and note we are considering the F2, so the force on the second wire here, and the magnetic field from the first wire is given by the Biot-Savart law. It's equal to the permeability of free space multiplied by the current in the first wire, so it's not the same current over here, divided by 2 pi multiplied by r. R is the distance between the two wires in this case. We combine everything together, so basically we replace B1 by this term, we get that formula over here. Note, often these wires are very long, so it might be useful to talk about the force per unit of length. So in this case, F2 divided by the length of both wires. Now, by the way, that's an assumption. We assume that both wires share exactly the same length. Otherwise, these formula kind of break apart, all right? So this is an important assumption. Both wires share the same length. All right, so F2 divided by the length is equal to the second current. Well, actually, added the L over here, that was wrong. Multiplied by the permeability of free space, multiplied by the first current, divided by 2 pi r. So that's it for the magnetic force between two current carrying wire. We will solve many examples involving this principle in the coming video. All right, so one last video, we are going to be tackling the solenoid, and after that we're going to be solving many examples. All right, see you in the next video.